Hey guys, so I'm making this video just so that way if anybody missed what we did today in class, today's Thursday, January 14th. So if you missed class or you just need help with problem set 2, I'm going to go over how to do impulse problems, so like the math stuff. But I'm going to cover everything from beginning to end so you can jump around to see the type of problem you need. Alright, but let's get started. So one thing that I did not cover in the last section of notes, like in the last note video, was what variables and equations that we use to calculate impulse. So these are important things to note, and you should definitely put these into like your notebook if you don't have them yet. Impulse, the variable we use for impulse is delta P. If you were to Google what symbol is impulse, you're going to get a couple different answers. One answer you might get is that they'll say, impulse is a capital J, or you might see imp. But here, I think the best definition or the best symbol to use is just delta P. Okay. The reason is because J is something that we use for energy, so it's already used for another concept. It's used in the calculation of energy, and imp is just long, and it sounds not like science. It sounds like a weird mythical being. So delta P is really descriptive, because if you remember, delta, well, it's actually written right here. Delta means change in, so if you put delta P, what you're saying is, what that means is the change in momentum, because little p means momentum. So I like this description because the literal definition of impulse is the change in momentum. So sorry about my handwriting there. I'm trying to squeeze it in here at the end of my little board. But yeah, that's why I like this symbol, because it makes the most sense. The change in impulse, or the change in momentum, because that's literally what impulse is. So that's why I like that one. Alright, so let me get rid of that real quick. So the next thing that you guys need to know are the units. Unfortunately, this is a little confusing. There are two different acceptable standard units that we use for impulse. Newtons times seconds, or kilograms times meters per second. Either one of these units will work in any given problem. They are literally the same thing. I know they look very different, but they do actually mean the same thing. I could do the like unit analysis for you right now if you really wanted to see it, but I don't think you're really that interested in the nuances of comparing units. So just know that Newton seconds, like N times S, is equal to kilograms meters per second. Just take my word for it. If you really want to know, you can ask me. I'll show you the math for it, but that's okay. So yeah, those two things are the same. They're both acceptable. Alright, and the first equation here that we're going to use is a basic definition equation. Alright, delta P equals PF minus PI. The change in momentum is equal to final momentum minus initial momentum. That's what it says right here. Okay, and that makes a lot of sense. Because a delta, which is this little triangle, delta means, as I already said, change in. Mathematically, what you should think of when you see a delta is F minus I. So if you see like delta P, that means PF minus PI. And later, you're going to see this one right here, where you have delta V. So you should think of delta V as VF minus VI. Okay? But we'll get to that equation here at the end of the video. So without further ado, let's look at some examples of this equation. Delta P equals PF minus PI. Okay. So, let's look at number 1. A car is traveling down a road with 6,400 meters, 6,400 kilograms times meters per second. It comes to a stop. Since it stopped, the final momentum is 0, because remember, this is a side note. Side note. Okay, let me write there. Side note, momentum is equal to mass times velocity. This is from our last section of notes. Remember this equation? So if your velocity equals 0 and you plug that into that equation, it doesn't matter what the mass is, your P will be equal to mass times 0, which anything times 0 is 0. So coming to a stop means momentum is 0. And you'll see things like this on the quiz where I might not tell you explicitly that momentum is 0. If I say it stopped, that should be implied that momentum is 0. So anyway, what is the impulse of the car? Okay, so let's go through this. Step number 1, remember we're using the problem solving procedure, so you should always start with making a list. So this variable right here, the car is coming down the road with this much momentum. So I'm going to call that PI because that is the momentum that the car is starting with. Okay. Then it comes to a stop. So the final momentum here, PF, is 0. Then the question is saying, what is the impulse? So impulse, we don't know what that is. That's what the question is asking. So that's our target. I give you the equation right here. And I'm going to do this for the first lesson or two where you're going to have more options in equations. As you can see, there's multiple equations for impulse. So I will help you out with this in the beginning. But think of this as training wheels. They're coming off at some point. But step 2 of the problem solving procedure is really easy because I'm helping you out with it, which is figuring out which equation to use. I already told you which one to use, so you can just copy that down. Alright, so that gives us, or leaves us with step 3, which is just to solve the problem. How do you do that? Well, plug in your numbers. Okay, so P, or delta P, we don't know what that is. We don't have any number for that, so we cannot change it. Final momentum, PF, is 0. Okay, so we plug that in. Alright, then minus PI, which is 6,400 kilograms times meters per second. Okay, well this is real simple. Just take 0 minus 6,400. that gives you negative 6,400. This is a rule, so the unit here will just end up being the exact same. This is a rule. I don't know if you know about this or not, but I will tell it to you now just in case you didn't know already. Here's a rule. When adding or subtracting identical units, they do not change. Okay? So this and this are identical, therefore we don't do anything to it. We just keep it exactly the same. Okay? So that's all that rule is saying. When you're adding or subtracting, nothing changes. It stays the same. Okay? And we just bring down our delta P, and there you go. That's our answer. Delta P is equal to negative 6,400 kilograms meters per second. Nice. Alright, I'm going to skip number 2 because that's pretty, I think you guys will be able to handle this type of things. You're just adding and subtracting. So let's look at this equation now. Alright, so this equation, if you remember, Newton's first law, way back when, we talked about this before winter break. An object in motion will stay in motion unless acted upon by an outside force. So what you can think of is what this law of motion is saying is you need a force to change velocity. Okay, so velocity is the measure of motion because it tells you what direction something's headed and it tells you how fast it's going. Therefore, velocity is essentially motion. So when we say motion, we're typically going to be referring to velocity. Alright, so if you need force to change velocity, and then you realize, you remember back to the previous section of notes where we talked about momentum being equal to mass times velocity. Well, if you need force to change velocity, then you're also going to need force to change momentum. So to change velocity, you need force. Therefore, to change momentum, momentum is P, you need force. Because velocity is part of momentum, so to change momentum, you need force. Okay? And that's what this equation is saying. All it's saying is that impulse, which impulse means change in momentum, is equal to the force times the amount of time that the force is acting. Okay? So you can think of it as like a car accelerating. Alright? So for this car to accelerate, we'll just ignore this one down here for now. Forget that's there. For this car to accelerate, to change its motion, it needs to exert force. To change its momentum, it needs to exert that force for a period of time. So for example, one common thing that people talk about with cars is like how fast they go from 0 to 60 miles per hour. Well, it needs to exert that force until its velocity equals that, which also means its momentum is going to be this times its mass. Okay, so force times time. Basically, what this comes down to is a force needs to act for a period of time. That's all I'm trying to say. I was going off in a long explanation, but this is all you need to know. Delta P equals F times T. Okay. So let's do an example problem with this. A tow truck applies a force of 2,000 newtons on a car for 3 seconds. What is the impulse? Okay, so we have step number 1, our list. So we have a force of 2,000 newtons. We have a period of time of 3 seconds. And it's asking what is the impulse, the change in momentum. So we don't know what that is. So our next step, we need to write our equation. Well, it's right here, so we can just copy that down. Easy. Okay, so step 3, let's solve this now. Plug in our numbers and solve. So delta P, well, we don't know what that is, so we can't change it. Here's force, that's 2,000 newtons. And multiply that by time, which is 3 seconds. Okay, so 2,000 times 3, that's 6,000 newtons. Alright, and we're multiplying newtons by seconds. So there we go. Just kind of put it the way it is. And there's your answer. Pretty simple. Okay, so that one's pretty straightforward. I think you guys won't have any issues with this type of problem. You just find your force, find the time, and multiply them together to get impulse. Easy peasy lemon squeezy. Alright, the final version of this equation that we're going to look at here is this one right here. Come on now. Okay, so this right here. Delta P, impulse, is equal to mass times delta V, change in velocity. Okay. So, I'm going to erase this real quick. It turns out that these two things, these two equations, are the same. They're just written in different ways. Okay, so here is proof to show you that delta P equals PF minus PI is equal to delta P is equal to mass times delta V. These are the same two things. Okay, what you need to keep in mind is that P equals M times V. So just momentum by itself is mass times velocity. Okay, so we can take that and substitute each of these P's for mass times velocity. Okay, so let's rewrite the equation with that substitution. Delta P is equal to, your final momentum would be the mass of the object times the final velocity of the object minus the mass of the object times the initial velocity of the object. Remember, we're only talking about one object at a time. So like this would be a car slowing down. The velocity of the car does not change from where it starts to where it ends. So this mass and this mass are equal. So we can do something that we call factoring out. So you draw brackets around there. You take the m, the mass from both of those terms, you bring it to the outside. That cancels these out. Okay? And so if you clean up this expression, like you get rid of some of this extra gunk in there, it would look like this. Okay? Delta P equals mass times Vf minus Vi. Now, if you were to distribute this mass like you would for anything being multiplied to parentheses, it would give you this expression here. Okay? So you can switch between these two things infinitely, and they mean exactly the same thing. Let me get rid of that. Maybe I shouldn't. My computer's running super slow today. Okay. So this is the same thing as this, because if you remember, delta equals final minus initial. So if you have delta V, that is equal to Vf minus Vi. Well, that's what we got right here. So you can just rewrite this bit right here can also be written as delta V. If you rewrite the whole expression that way, delta P equals mass times delta V. So in short, this is this. They are the same. My recommendation is that you write down this version in your notes somewhere, because this will be very helpful for you. Delta P equals mass times Vf minus Vi. Okay. But also just remember that anytime you see delta, it equals F minus I. Change in something is the final minus the initial, okay? Because that's the key to this. So let's look at some of these problems here. Oh, hello. Okay. Come on. Hello. There we go. Okay. So let's go through this. Let's do number 5. 1,200 kilogram car traveling down the road at 30 meters per second. But then it comes to a stop. So its final velocity is 0. What is the impulse? Alright. So let's start like always. Make our list. So mass is right here. That is equal to 1,200 kilograms. Our initial velocity is this number, because that's what it starts at. We're starting at 30 meters every second. But then it comes to a stop. Okay, so at the end it is at 0 meters per second. And the question is asking what is the impulse. Alright, sounds straightforward enough. Here is our equation. Delta P is equal to mass times change in velocity. But remember, this expression is the same thing as writing this. Okay, so that way you can plug these numbers in. So Step 3, let's solve this. Let's plug our numbers in. Alright, delta P we don't know, so we can't change that. It's just going to stay that way. Mass is 1,200 kilograms. Alright, now let's multiply that by the difference in velocity, which is 0 meters per second minus 30 meters per second. 0 minus 30 gives you negative 30. This is order of operations, by the way. So before distributing or anything, you should just solve what's inside the parentheses. So as you can see, everything stays the same. I just simplified inside the parentheses before doing anything else. Okay, so now we need to take negative 30 times 1,200, and I'm just going to write this up here. So up here. So we have our delta P is equal to, that would be negative 36,000. Hang on. I don't like that. That looks messy. Delta P is equal to, I'm just going to go to the side, is equal to negative 36,000. And then you just put these two things together, kilograms times meters per second, because they were being multiplied together. Okay, there you go. Let's do another slightly more sophisticated example. Alright, so we have a bullet traveling at this 500 meters per second, and then it stops. There's an impulse of negative 50. What is the mass? Okay, so start with our list. Okay, so before anything happens, our initial velocity of the bullet is 500 meters per second. Our final velocity, the bullet comes to a stop, so that is 0 meters per second. The impulse, the delta P, is negative 50 newtons times seconds. What is the mass? Well, we don't know. So that's what we got to figure out. Here's step 2. Here's our equation. Okay, delta P equals m times delta V. You could also write this again, same thing as up here. Delta P equals mass VF minus VI. Okay, they're the same thing. Alright, so let's plug in our numbers and solve. Okay, so delta P is negative 50 newtons times seconds is equal to mass. Well, we don't know what mass is, so that's got to stay the same. VF minus VI. Alright, what's VF? VF is 0. VI is 500. Alright, so take 0 minus 500, because remember, if our target is this thing, our target is M, we need to get it by itself, but before doing anything fancy, we should just make this more simple. Anything inside the parentheses should go first. Okay, so 0 minus 500 gives you negative 500. The units are identical and we're subtracting, so they don't change. I'm going to multiply that by m, and our impulse stays the same because nothing has happened on this side of the equation yet. Okay, so we need to get mass by itself. We're multiplying mass by this number. If they're being multiplied, the way to get the m by itself is by doing the opposite of multiplication, which is division. So we will divide both sides of the equation by this number. Okay, and that will give us, I'm just going to go off to the side right here. That gives us negative 50 divided by negative 500 is positive 0.1. Okay, and we are solving for mass, so you should know that mass is in kilograms. Okay, this unit, these units kind of look a little weird, and you might be wondering, well, how do you end up with kilograms from this? There's no kilograms in there. Well, there actually is. This is kind of a side note. Again, I'm just trying to show you that this does work out. Okay, so if you remember back from last unit, newtons is equal to kilograms times meters per second squared. So if we take this and replace the newtons here with this phrase, or this term, that would be kilograms meters per second squared times seconds over meters per seconds. This looks very complicated. Okay, so we have this seconds here is in the bottom of a fraction. The trick is that flips up, which will leave you with a second squared up here. So we have a seconds squared here and 1 at the bottom of this fraction, so those cancel. Then we have a meter at the top of this fraction and at the bottom, so those cancel, which just leaves you with kilograms. So that's how you get kilograms out of this whole mess. But you don't have to worry about this kind of stuff. Just realize that if you're solving for mass, you should have kilograms. That's it. Simple as that. Don't worry about all this mess. Alright, sorry for this video being super duper long, but I hope it was helpful, and yeah.